today I am going to request one of the students who has attended this course, namely Tony Sebastian, to make a presentation on the excellent application presentation that he worked upon in this course. I shall not take away from him the thunder of explaining what he did, save to give an introduction in a few lines. I shall just introduce the broad theme of his application, and the broad theme relates to what is called denoising. Now, denoising, as the name suggests, means an operation of separation of wanted and unwanted in a mixture of signal and noise. As expected, normally the noise or the perturbation is unwanted, and it is often the case that when one goes into the wavelet domain, particularly in the context of biomedical signals, it is easier to separate the wanted signal from the unwanted noise. We could have several instances of this, but what we have today is essentially a suppression of respiratory artifacts, which Tony would explain to you on his own. So, now I introduce Tony Sebastian, and I request him to make a presentation on his work related to the suppression of these kinds of artifacts and wavelet based denoising.
Hello everybody, myself Tony Sebastian of second year MTech student of Biomedical Department, IIT Bombay. Welcome to my application assignment presentation on wavelet based denoising for the suppression of respiratory artifacts in impedance cardiogram signals. Now, the technique I am going to present here was originally developed by Dr. Vinod K. Pandey and Professor P. C. Pandey of EE Department, IIT Bombay. Now, what is impedance cardiography? Impedance cardiography is a non-invasive technique for monitoring stroke volume and other cardiovascular indices, and thereby obtaining diagnostic information on cardiovascular functioning by sensing the variations in thoracic impedance due to the change in blood volume. Now, since most of you are from engineering background, many of the technical terms in this definition are not familiar for you. So, it is better to have some basic understanding of the heart structure for getting into this definition, and hence for the better understanding of the project. Now, let us look into the structure of the heart. Now, this is the structure of the heart most of you may be familiar with, but this is not how the heart looks like. Let us look into the actual structure of the heart. Now, this is how the structure of the heart looks like. Thanks to my friend Ajay Tijore for drawing such a wonderful diagram for this presentation. And now, let us look into the structure of the heart with an engineer's perspective. We can visualize heart as a combination of 4 chambers. Here you can see one chamber, that is the right atrium. Here you can see the second chamber, that is the left atrium. Now, here is the right ventricle and here is the left ventricle. Now, the right side of the heart, that means the left hand side of the picture, deals with the deoxygenated blood, and the left side of the heart, that is the right side of the picture, deals with the oxygenated blood. Now, these 4 chambers can be visualized as a combination of 4 pumps. It is very similar to the mechanical pumps. The function is just to pump the blood. Now, blood from the different part of the body will enter into the heart to the right atrium. Now, here you can see the 2 major vessels, that is this one and this one. These are the superior vena cava and the inferior vena cava. Superior vena cava will be bringing blood from the upper part of the body to the heart, and inferior vena cava will be bringing blood from the lower part of the body to the heart. Now, the name superior and inferior is not because of its functioning, it is just because of the position. Now, as soon as this right atrium filled with blood, this blood will be, right atrium will pump the blood to the right ventricle. There is a valve separating the right atrium and the right ventricle, that is known as that is this valve, that is the tricuspid valve. Now, from this right ventricle will pump blood to the lungs for getting oxygenated. As you know, blood which is coming from different part of the body to the heart has carbon dioxide in it, and we need oxygen in the blood for the body functioning. Now, in the lungs, this blood will exchange carbon dioxide and oxygen. For that, this right ventricle will be pumping blood to the lungs through the pulmonary artery. This is the pulmonary artery. So, right ventricle will be contracting in this direction, and by that time this tricuspid valve will be closing and this particular valve will be opening. This particular valve is known as semilunar valve. Because it is opening to the pulmonary artery, it is known as pulmonary semilunar valve. So, blood from this right ventricle will pump to the pulmonary artery and it will go to the lungs, and from the lungs blood will come back to the heart to the left atrium. So, blood will come back from the heart, from the lungs to the heart through this pulmonary vein to the left atrium. Left atrium is on the top side. So, from this left atrium, blood will be pumping into the left ventricle. There is a valve separating left atrium and the left ventricle, that is known as the mitral valve or bicuspid valve. Now, comes the most important part of the heart. Left ventricle, out of these 4 chambers, I say left ventricle is the most important part, because left ventricle will be pumping blood to the different part of the body. As you know, since our body parts are far away from the heart, it has to do a lot of work for pumping blood to the different part. So, this left ventricle will be contracting with maximum force, and when it is contracting, this particular valve will be opening. This valve is again a semilunar valve, which is the aortic semilunar valve, because it is opening to the aorta, and from this left ventricle the blood will be pumping to the aorta. Aorta will be taking away blood to the different part of the body. Here you can see different branches of this aorta. Now, here you can see the beauty of this cardiac design. I say the beauty because, see, compared to all the other chambers, left ventricle has to do maximum work. For that, this particular muscle has maximum thickness compared to the other valves, other chambers. Now, another important factor here is why left ventricle is important is, see, even if this atrial muscles have some problems, or even if this atrial pumps are not working, because of the gravitational force and because of the weight, this tricuspid valve and bicuspid valve will automatically open, and 70% of the blood will automatically fall into the ventricle, even if this atrial pumps are not contracting. So, we can say disorders related to atrium are not comparatively that much danger compared to the disorders related to ventricle. Now, let us look into some of the waveforms related to heart. This upper dotted line indicates the aortic blood pressure. That is, when we are measuring our blood pressure by using normal pressure meter, we will be getting this aortic blood pressure. That is, when we are going to hospital, the doctor is measuring our aortic blood pressure by using his normal pressure sensors, and this blood pressure what we are normally getting for a healthy man, 80 to 120, that is the systolic and diastolic pressure of the aorta. Here is the aorta, you can see, because normally our doctors are measuring blood pressure in the hand. This blood pressure is slightly, whatever pressure we are measuring is slightly lesser than the aortic pressure, but it gives an approximate measure of aortic blood pressure. Now, the second waveform is the ventricular blood pressure and the third one is the aortic pressure. Now, at the initial phase you can see aortic pressure is little bit higher than ventricular blood pressure. Now, when this aortic pressure is higher than ventricular pressure, this tricuspid valve as well as the bicuspid valves are open, and at this time this left atrium and the right atrium are contracting and blood will be falling to the ventricles. Now, as soon as this ventricles start contracting, pressure inside ventricle will increase, start rising, and at some particular point it will overcome aortic blood pressure. At that particular moment, this aortic valve, this tricuspid valve and semilunar valve will be closing because the pressure inside the ventricle is higher. So, this valve will be closing and it prevents the backflow, and the pressure inside ventricles will be start again and building. At some particular point it will overcome the pressure inside aorta, and at that particular moment this semilunar valve will be opening and ventricle will be pumping blood into the aorta. This will be continue for a moment. When this ventricle start relaxing, the pressure inside the ventricle start reducing. When this ventricular pressure becomes lower than the aortic pressure, this aortic valve will be again closing and ventricle starts relaxing, the blood flow stops. Now, this ventricle pressure again will come down, and when it comes down below the aortic, the atrial blood pressure, this tricuspid valve again will tricuspid valve and bicuspid valve again will open and blood will again come to ventricle, and this cycle will be continuing. Now, the next waveform is aortic flow. As you can see, this particular point is the point at which the aortic valves are opening, the semilunar valves are opening, and at this particular moment blood flow to the aorta starts and it will be a pulsatile flow. You can see the if you try at our radial artery or some particular points, you can see the pulsatile flow, you can feel the pulsatile flow of the blood. This will be pulsatile, and when this particular valve is opening, blood flow will be for a sudden blood flow will happen, and it will continue for a moment, and once the valve closes, flow again stops. Again in the next cycle it will be continuing. The next two waveforms we will be looking a bit later, and the next waveform, this particular waveform is the most common biosignal, and most of you might be familiar with this particular waveform. This is the electrocardiographic waveform. In most of the films, the climax scene will be some ECG waveforms will be coming. Some ECG waveform will be coming, and once the waveform will be stopping, that will be the end of the story. So, this waveform, particular waveform, this electrocardiographic signal gives a measure of the electrical activities of the heart. This particular waveform I will draw once again and I will explain. Now, basic electrocardiographic signal will be looking something like this. So, this is the P wave, then QRS and a T wave. This P wave indicates the beginning of contraction of the atrial pumps. So, as I show in the previous picture, the atrial pumps will be start contracting at this axis is the time axis. So, in each cardiac cycle, at this particular moment the atrial pumps will be start contracting, and this QRS complex indicates the contraction of ventricles. So, atria contracted, at this particular moment the ventricular pumps are start contracting. When the ventricular pumps are start contracting, the upper pumps again start relaxing. At T wave, the ventricular pumps are relaxing. So, By looking at an electrocardiographic signal, a cardiologist can tell how good a heart is working, or what are the major disorders of a heart we can tell. Now coming back to the previous picture. So this gives a measure of electrical activities of the heart. Now the last one is the phonocardiogram, that actually gives the cardiac sounds. Cardiac sounds mean our doctors basically by a stethoscope they are hearing these sounds. These sounds are actually sounds of closing of these valves. First sound is the closing of these aortic valves, and the second one is the closing of this semilunar valves. Now we will go back to impedance cardiography, our technique. Now for impedance cardiography, we will place 4 electrodes like this in the body, and we will be injecting current through the upper 2 electrodes. That means we will be basically injecting a high frequency current of very low amplitude, and we will be measuring the potential voltage difference between these 2 particular moments, and we will find out the impedance variation across these 2 particular points. This area is the thoracic region. Now we will go back to the previous picture and understand the 2 waveforms which we kept aside. Now these are the 2 waveforms we kept. This one is the delta Z, that means the impedance variation because of the blood flow, because in every body part, in every body part in the thoracic region there are basically 3 types of conductive tissues. That is, first one is the in this area basically we can see 3 different types of tissues. One is the rib cage, you can see something like this. We have ribs, this side and this side, rib cage, bone, these are bones, these are basically non-conductive. Then here we will be having the lungs. Lungs are muscle tissues, soft tissues, they are conductive but not that much conductive compared to blood. And next one will be the vena cava and the thoracic aorta. Vena cava will be somewhere here and aorta will be here. And compared to all the other body fluids or body parts, blood is more conductive. If, for example, if you say conductivity of blood is 150, then conductivity of lungs and other muscles are 1500 or 10 times lower compared to blood. So whenever the heart is pumping, what will be happening? This aorta will be changing its dimension. Now because of that, the voltage we are measuring changes, and we can find out the impedance variation from that. Now this is how the impedance variation looks like. Whenever the aorta is open, that means blood is pumping to the aorta, its dimension changes and the impedance go down, resistance go down. So here you can see a fast change in the impedance, and it will again come down. Again in the next cycle the same variations will happen, and the time derivative of this particular waveform is known as the impedance cardiogram signal. By using certain parameters measured from this impedance cardiogram signal, we can find out stroke volume and, as we told, other cardiovascular parameters. The 3 major points in this particular waveform are the B point, the C point and the X point. These 3 points are the major points in this particular waveform, and this is the time derivative of this impedance waveform, and this is known as the impedance cardiogram signal. Now coming back to the slides for finding out how to estimate the stroke volume. Now for estimating the stroke volume, we have a special formula developed by Kubicek et al. That formula is stroke volume. Here in the slide you can see stroke volume is equal to rho into L square divided by Z naught square into negative of dz by dt max into TLVET. Now let us spend a minute in understanding this formula. Rho is the resistivity of the blood, that's a constant, that is somewhere around 150. Then L is the distance between the electrodes, as we show in the previous picture. The distance between these two electrodes are the L. That is the we are actually modeling this thorax as a conductor. So the distance between these 2 points is L. Now the next parameter is the Z naught, that from the previous picture. This delta Z will be above a particular base value. So that particular base value is Z naught. Normally it is around 25, but it varies from patient to patient. And the next parameter is dz by dt max. Dz by dt max, this is the dz by dt waveform. Dz by dt max is not the difference between the C point and X point, but it is actually the difference between B point and the C point. Now B point, what is the significance of B point and X point? See, here comes the significance of the other waveform. See, B point indicates this particular point. This particular point is the point at which ventricular pressure is above the aortic pressure. That means this is the particular moment at which the aortic valves are opening and the blood is pumping into the aorta. And X point is this particular point, and at this particular point ventricular pressure will be again come down below the aortic blood pressure, and at this particular moment this valve will be closing. So during this period, that means the time period from which B point to X point, aortic valve is open, and this is the particular moment in which aortic valves are opening, and this is the duration in which ventricles are pumping blood into the aorta. So TLVET is basically the time difference, the point difference between time duration between B point and X point. So from this waveform, impedance cardiography waveform, we will be basically taking dz by dt max as well as TLVET. Now the other major parameters related to heart, they are stroke volume. Stroke volume is basically the amount of blood pumped by heart in during one heartbeat. That is during which this aortic valve is open, what is the amount of blood pumped by the heart in one cardiac cycle. And the second parameter is cardiac output. Now cardiac output is the amount of blood pumped by heart in 1 minute. That is basically in stroke volume multiplied by heartbeat. That is, we can see by counting, just by counting number of C points, or C points will be very easy to detect, and by counting the number of C points, or by counting the QRS complex in the ECG diagram, we can get the heart rate, and then by multiplying stroke volume into that particular value, we will be getting cardiac output. And next parameter is left ventricular ejection time, that is basically the time difference between the B point and X point. Next parameter of interest is systemic vascular resistance, that is the resistance offered by aorta to the blood flow. And the next cardiovascular indices is left cardiac work, that is, as I told you, we are basically, among all the cardiac parameters, we are basically interested in this part of the heart, that is left ventricle, the work done by this part of the heart for pumping blood into different part of the body, that is the left cardiac work. Now coming back into the artifacts, impedance cardiography signal basically have few types of artifacts. What are artifacts? Artifacts are actually man-made signals which are not necessary, which are unnecessary in impedance cardiographic point of view. Now we have two types of artifacts major artifacts are the respiratory artifact and the motion artifact. Now, respiratory artifacts are very low in frequency, that is basically from 0.04 hertz to up to 2 hertz, and motion artifacts are up to 10 hertz. Now, if we analyze the impedance cardiographic spectrum, we have signals of interest from 0.1 hertz, 0.8 hertz up to 20 hertz. Now, here you can see that this motion artifact and respiratory artifact has signal components components in the same band. Now, we are actually looking into, here in this particular presentation, we are looking into respiratory artifact suppression. Now, in this particular picture, you can see a signal in an impedance cardiographic signal recorded during exercise. So, this is an ICG waveform recorded from a healthy subject during exercise. So, this particular signal has both respiratory and motion artifacts. Now, these particular peaks, high peaks, are because of motion, and this slow varying baseline is because of respiration. Now, what is the disadvantage of these artifacts? Here you can see when we are finding out dz by dt max, these particular points will be coming into picture and they will be introducing severe errors, and because in the formula we are using this dz by dt max, this will introduce severe errors for calculating stroke volume. Also, this baseline drift also introduce errors in dz by dt max, also in TLVET calculation. So, it is very important to suppress these artifacts for the proper estimation of stroke volume and other cardiovascular indices. Now, the project objective is to investigate different denoising techniques for the suppression of these artifacts and study in detail the wavelet based denoising technique for the respiratory artifact suppression, and investigate few different wavelets and see how these wavelets are useful in this denoising applications. Now, there are different methods of artifact suppression. The first technique is breath hold. Now, you can see the respiratory artifact is because of respiration. So, the easiest way or the simplest way of respiratory artifact cancellation is holding the breath. Now, the problem with breath hold is when we are holding the breath, cardiac activity will always go down. And another problem is when we are recording the impedance cardiogram after exercise, it is difficult to hold the breath, because after the exercise cardiac activity will be more, so it is difficult to hold the breath. The second established technique is ensemble averaging. The problem related to ensemble averaging was proposed by Howritz et al. In 1990. The problem related to ensemble averaging is it will distort the waveform, or it will remove the beat to beat variability in the impedance cardiogram. Actually, we are interested in stroke volume as well as the variation in the stroke volume. In each beat, how much variation is coming in the blood. That gives the that makes the sense in diagnosis. Now, when we are doing ensemble averaging, it may blur this B point, X point, and so we won't get, after ensemble averaging, we won't get this clear B point and X point, and hence it will introduce distortion or errors in calculating the stroke volume. Next technique is adaptive filtering, which is developed by Professor P.C. Pandey and Vinod K. Pandey again in 2005 in IIT Bombay. The problem with adaptive filtering is always good in biosignal denoising if we have a reference signal. But for adaptive filtering, we need to have a reference signal. For that, we have to keep a pressure sensor in the nostril. So, this is again a problem of patient complaints. That is how adaptive filtering works. Then the next technique is the one which we are working on, is wavelet based denoising, which is known as the level dependent thresholding, which is again developed by Pandey and Pandey in 2007. Now, in wavelet based denoising, selection of wavelet basis is very important. Why selection of wavelet basis is very important? in denoising applications, it is observed that basically in whether it is in ECG denoising or in ICG denoising, it is observed that if the wavelet and the waveform has some similar shape, then the denoising is better, always better. So, in ECG denoising or in ICG denoising, there are some particular wavelets which has some shape similarity with biosignals. Those wavelets will be giving better denoising, better separation of noise and the signal. Now, let us see some waveforms. This is the experimental setup of impedance cardiography. Here you can see the recording of impedance cardiogram. 4 electrodes are placed over here, 2 in the upper part and 2 in the lower part. This is the impedance cardiograph, and through the upper 2 electrodes current will be injecting, high frequency current of low magnitude will be injecting, and this will be measuring this lower 2 electrodes will be used for measuring the voltage, and hence we will be calculating the impedance variation. Now, this impedance cardiograph, this particular impedance cardiograph is the HIC 2000 impedance cardiograph from bioimpedance technology. Now, we have acquired the signal at sampling rate of 500 hertz. Signals are recorded both in resting condition as well as signals recorded by performing different activities. One signal which we saw before is while performing some activity. Now, this is the basic wavelet decomposition. The original waveform is sampled at 500 hertz. Now, each detail gives a band pass signal and each approximation gives a low pass signal. Now, when we are decomposing the signals into different levels, for example, if we are decomposing the signal into 8 levels or 9 levels, the first decomposition, if the sampling rate is 500, it will be having signal components up to 250 hertz because of Nyquist criterion. So, the first detail will be having components from 125 hertz to 250 hertz, and the approximation will be having signals from 0 hertz to 125 hertz. Second detail will be having components from 62.5 hertz to 125 hertz, and second approximation will be having components up to 62.5 hertz. Similarly, in 8th level detail, it will be having components from 0.98 hertz to 1.95 hertz, and approximation will be having components from 0 to 0.98 hertz. Now, in this particular method, what we are doing is we are decomposing the signal into different level, and we are also decomposing the artifact into different components, and we are seeing up to what level the signals are present and up to what level the artifacts are present. Now, we use different wavelets for the decomposition, and this is the 10 level decomposition of an ICG signal, which is shown here by using the Coeflet 5 wavelet. Here you can see detail 1 and detail 2, they do not have much component, detail 3 they do not have much components because we do have components only up to 20 hertz. These are high frequency components, we do not have any signal or artifact in this area. And from the fourth approximation, fourth detail onwards, we have signal components, 5th, 6th, 7th, up to 10, all the approximation, all the detail and approximation. This is an ICG recorded under breath hold condition. So, it is not having any artifact, it is having only purely signal component. So, all the 10 detail and approximation has signal components. So, we cannot use this particular wavelet for the separation because it is not capturing signal components in any particular detail, because see 8th level detail or 9th level detail are very low frequency components. So, this will be having, even if the signal is supposed to have a respiratory artifact, this will be having signal as well as D9 will be having, D9 and D10 will be having signal as well as artifact. Now, this particular waveform is the 10 level decomposition of same ICG using the Watch 6 wavelet. Again, you can see all the 10 detail and the approximation has signal components in it. Now, here comes the one which we are interested in. This is the 10 level decomposition of the same ICG by using D-May wavelet, that is the discrete Mayer wavelet. Now, here you can see D1 and D2, D3 as such they are high frequency components, we don't have any components in that part. D4, D5, D6, D7 and D8 has signals in it, but in D9, D10 and A10 we don't have any signal components. So, this is basically D9 is the low frequency area, that is from 0 to 0.98 Hertz. So, here is basically in this frequency band the respiratory artifacts are coming, and in this particular session we don't have any signal component. So, this particular wavelet will be very useful for separating the signal and the artifact. So, in our denoising technique we will be basically adding this first 8 details and we will be removing D9, D10 and A10 for the artifact suppression. So, the artifacts free ICG signal is obtained by adding D1, D2, D3, D4, D5, D6, D7 and D8. Now, further studies at SPA lab showed that similar results this obtained by DMA wavelet can be achieved by using one more wavelet, that is similar 26 wave also gives similar result as obtained by DMA wavelet. Here you can see one ICG waveform recorded under resting condition but with respiration. This first waveform is the ICG recorded with respiratory artifact. The slow varying oscillations are because of this respiration, sinusoidal oscillations are because of the respiration. Now, the second wave is denoised ICG waveform by using DMA wavelet, that is we have decomposed the signal into 10 levels by using DMA wavelet and reconstructed the signal by using first 8 details. And the third one is same procedure followed by using similar 26 wavelet. By visually we can see both the wavelets are giving same performance. Now, the fourth one is the artifact which is extracted from the ICG waveform by using DMA wavelet. This is basically first waveform minus the second waveform, that is the first waveform which has artifact and the second one is the denoised waveform. The difference is basically the artifact signal, and the last one is the respiratory artifact removed by using similar 26 waveform. Here you can see both the wavelets are capturing exactly same artifact and exactly the same signals. Now, why this happens? See here we can see the wavelet and scaling function of DMA wavelet and similar 26 wavelet. Here DMA wavelet has 1 or 2 samples in the wavelets compared to similar 26 wavelet has 52 in it. Now, here you can see it almost has same shape. We can see a shape similarity in DMA wavelet and similar wavelet. Both the mother wavelet and the scaling function has similar shape for DMA wavelet and similar 26 wavelet. Because of this similar shape similarity only we are getting same result for both the wavelets. Now, this is a basic block diagram of wavelet decomposition by using filter banks. Here you can see we will be having filters, low pass filter, decomposition filter, and again here after this here we will be getting wavelet coefficients, and for getting the details back we have to use the reconstruction filter of same length again. Here you can see the advantage of using similar 26 wavelet, because similar 26 wavelet is having only 52 coefficients compared to DMA wavelet having 1 or 2. So, since we are using 10 level decomposition, if we use similar 26 wavelet, the calculation complexity will be comparatively very less compared to DMA wavelet. Now, coming back to the summary of the presentation, we can see that both similar 26 wavelet and DMA wavelet are giving better performance in artifact suppression, and they are giving almost similar performance compared to other wavelet, and we studied different wavelets like Koflit wavelet and Dobach 6 wavelet. They were not comparatively that much good compared to these wavelets, and similar 26 Advantage of similar 26 wavelet is it reduces the calculation complexity because of it is having low number of filter coefficients. Now the future work will be we can study the applicability of wavelet in denoising motion artifacts, and also we can investigate whether any other wavelets are giving in denoising application. What you can try is you can use this technique or similar technique for the denoising of ECG denoising, because ECG data files are available in MITB database. You can download some ECG database data signals from MITB database, and you can try similar kind of technique in denoising of ECG signal. ICG signals are till now it is not that much popular compared to ECG signal, so we don't have any open database compared to ECG signal. So you can download some ECG signals from the MITB database, and I hope you all will try some of the denoising techniques. Maybe these techniques may not be applicable, but some modification of this may help in denoising ECG signal denoising also. So you can try that kind of denoising. And these are few reference papers we have referred. The first paper is Kubicek et al.'s paper. They proposed the impedance cardiography technique itself, and the few other reference papers are denoising techniques and signal processing techniques. If you are interested in further studies, you can refer to these papers and get more information on this denoising technique and more about impedance cardiography technique. That's all about the presentation. Thank you.